You think you know what a force is. You think when you push two magnets together and feel that invisible rubbery resistance, you are feeling a force, like a push, a shove. Wrong. That push is a lie. If I told you that the reason those magnets repel isn't because of energy or charges or fields, but because of information, would you believe me? Probably not. It sounds crazy. But try this. Do this right now. Imagine holding two strong magnets, north to north. You push. The air between them feels solid. It pushes back. You assume something is there, but there is nothing there. What you are actually feeling is the universe protecting its own source code. You are feeling a fundamental law of quantum mechanics screaming error. You are feeling two electrons refusing to be the same person. See, the standard explanation, like poles repel, is garbage. It's a label, not an answer. It tells you what happens, not why. To understand the why, we have to break the concept of touching. We have to shatter your idea of what matter is. Because when you push those magnets together, you aren't fighting a force field. You are fighting the architecture of reality itself. Let me show you. Go find two magnets. Seriously. If you don't have them, close your eyes and imagine holding two heavy ceramic magnets. You bring the north poles together. Push. What do you feel? It's spongy, right? It feels elastic, like there's a rubber ball trapped between them. You push harder, the resistance fights back harder. It's smooth. It's perfect. It feels distinctively physical. But stop. Look at the space between them. There is nothing there. If you did this in a vacuum, if you sucked out every single molecule of air, it would feel exactly the same. So here is the paradox that should keep you awake at night. How can nothing be solid? How can empty geometry have stiffness? Your brain tries to rationalize it. It says, oh, it's a force field, like in Star Trek. But force field is just a lazy label. It's a word we use to stop asking questions. Here's the part nobody tells you. That springiness, that resistance, it isn't a force in the way you think of a force. It's not a simple shove. What you are actually feeling is a traffic jam, a quantum traffic jam. You are trying to force two things into the same state, and the universe is literally bending space and energy to stop you. The empty space becomes solid because it has to. But to understand why this invisible wall appears out of nowhere, we have to look at the bricks in the wall, the electrons. And to do that, we have to destroy the biggest lie your high school chemistry teacher ever told you. They told you electrons spin like little planets. Wrong. Let me show you what they actually do. Picture an electron. I bet I know what you're seeing. A tiny little blue ball whizzing around the center of an atom like a planet around the sun. And, crucially, you picture that little ball spinning on its axis, like a basketball on a finger, like the Earth. Stop. Delete that image. Burn it. It's wrong. It's not just a little bit simplified. It is physically impossible. Here is the math nobody shows you. Electrons are incredibly small. If an electron were actually a physical ball, and it had the magnetic strength we know it has, its surface would have to be moving faster than the speed of light to generate that field. Wait, faster than light? That breaks relativity. Einstein would roll in his grave. So, the electron is not spinning. Nothing is moving. Nothing is rotating in physical space. Yet, it has angular momentum. It has all the mathematical properties of a spinning object without actually spinning. This is where your intuition fails. In our world, spin is a verb. It's something you do. In the quantum world, spin is a noun. It's something you are. Think of a ripe tomato. It is red. Is the redness moving? Is the redness spinning? No. The redness is just a property of the tomato. The tomato has redness. An electron has spin. It is an intrinsic label, a permanent tag attached to its existence. It's just there. And here is the kicker. In our world, a basketball can spin at any speed, fast, slow, wobbly, but an electron, it has only two settings. It can be spin up or it can be spin down. That's it. No stopping, no slowing down, no 45-degree angles. It creates a pixelated reality where the electron is either pointing north or south, or why does this matter? Because magnetism, that force you feel in your hand, is just the macroscopic sum of all these billions of tiny impossible spins lining up. But there is a problem, a massive problem. What happens when you take two of these electrons, two of these identical spinning ghosts, and try to put them in the same place? You run into the scariest fact in the universe, indistinguishability. Let me show you why nature panics when things look too similar. Let's play a game. Imagine this. I have two identical ping pong balls. I paint a tiny 1 on the first ball and a tiny 2 on the second ball. I put them in a box. I shake the box. You look inside. Even if they look identical, you can still tell them apart. You see the numbers. Ah, there is ball 1. There is ball 2. Easy. Now, let's erase the numbers. They are perfectly white. Identical mass, identical shape. I shake the box. You look inside. You point to 1 and say, that was the one on the left before. Maybe you're right. Maybe you tracked its path with a high-speed camera. In our world, the classical world, you can theoretically track every object. They have a history. They have a path. Wrong. In the quantum world, this logic collapses. Electrons don't have serial numbers. They don't have names. They don't even have continuous paths you can track. If I have two electrons in a box, and I look away for a nanosecond, and then look back, it is fundamentally impossible, not just hard, impossible to know which is which. Did they switch places? Did they stay put? The universe doesn't just not know. The universe says it doesn't matter. This sounds trivial. Who cares if we can't tell them apart? Here is the thing. Because they are identical, nature treats them as a single system, a single entity. If I swap two electrons, the physical state of the universe should look exactly the same, right? If I swap my car for an identical car, nothing changes. The universe doesn't care. But electrons are fermions, and fermions are the drama queens of the particle zoo. When you swap two electrons, the universe does notice. The math doesn't stay the same. The wave function, the mathematical description of their existence, flips its sign. It goes from positive to negative. Wait, if I swap them, the math gains a negative sign? Just from switching seats? Yes, it's called being anti-symmetric. And this tiny little minus sign, this mathematical glitch, it is the reason you are solid. It is the reason you don't fall through the floor. It leads to the most important rule in all of chemistry, the rule that bans twins. Let's meet the most stubborn man in physics, Wolfgang Pauli. In 1925, he proposed a rule so simple it sounds like common sense. But in quantum mechanics, common sense is a trap. He said, no two fermions can occupy the same quantum state simultaneously. This is the Pauli exclusion principle. Think of an atom not as a solar system, but as a concert hall, the grand hotel of the universe. Imagine this. You walk into the concert hall. There are rows of seats. Each seat has a number. Row 1, seat A. Row 1, seat B. Now, electrons are the audience. Here is the rule. Only one electron per seat, period. If an electron is sitting in row 1, seat A, spinning up, no other electron in the entire universe can sit in row 1, seat A, spinning up. Stop. Think about that. If I try to force a second electron into that seat, what happens? Does it just squeeze in? Does it sit on the first electron's lap? No. The universe physically prevents it. It is impossible. If I want to put a second electron in that same energy level, I have to change something about it. I have to flip its spin. Remember? Up or down. So, one seat can hold two electrons if one is spinning up and one is spinning down. They are distinct. They are different. The universe allows it. But what if I have a third electron? Both spins are taken. Up is taken, down is taken. Where does the third electron go? It can't squeeze in. It is forbidden. So it has to go to the next row, row 2, a higher energy level, a more expensive seat. This is why atoms have structure. This is why chemistry exists. This is why you are not a tiny black hole of collapsed matter. Because electrons are forced to stack up, layer by layer, filling shell after shell, pushing outwards. Here is the twist. This isn't a force like gravity. Gravity pulls. Electromagnetism pushes and pulls. The exclusion principle isn't a force. It's a traffic law. It doesn't push. It simply says no. But when you bring two magnets together, you are trying to break this law. You are trying to force electrons into occupied seats. And the penalty for breaking this law? Energy. Let's stop being polite and look at the chaos. Up until now, we've talked about balls and seats and rows. Nice, clean analogies. Wrong. That's too simple. Electrons are not balls. They are clouds. Imagine a cloud of smoke. It spreads out. It dissipates. It has no hard edge. Now imagine two clouds of smoke. What happens when two smoke clouds drift into each other? They merge. They mix. They become one bigger cloud. That makes sense, right? Waves reinforce each other. But electrons are fermions. Remember that word? Fermions are antisocial. They hate each other. When two electron clouds, their wave functions, try to occupy the same space, something very weird happens mathematically. They don't mix. They subtract. The wave function of one electron minus the wave function of the other. Result? 0. This is the part that breaks your brain. The probability of finding two electrons in the same place goes to 0. It vanishes. Think about a guitar string. You pluck it. It vibrates. Now imagine pinching the string at a certain point so it stops moving there. That point is called a node. When two electrons try to overlap in the same state, the universe pinches the fabric of reality between them. A node forms, a dead zone, a forbidden gap. The probability cloud doesn't just get crowded, it gets erased. Now watch what this implies. If the probability is 0 in the middle, where do the electrons go? They are pushed away from the center. They are squeezed out to the edges. They are forced to be farther apart than they want to be. They are effectively repelled, not by a force field, but by a mathematical impossibility. It's like trying to push the north poles of two magnets together and feeling that invisible barrier. That barrier is the universe saying, the probability of you being here is 0. Go away. But here is the catch. This repulsion isn't free. Moving electrons away from the comfortable center requires energy. Nature is lazy. Nature wants to be in the lowest energy state possible. So when you try to shove these clouds together and the universe forces them apart, the energy of the system shoots up. It costs energy to fight the math. It costs energy to fight the exclusion principle. And that rising energy cost, that tax you have to pay, that is the feeling of repulsion. But why does it feel like a spring? Let's do a thought experiment. Imagine a very simple game. You have a box. You drop a marble in. Where does it go? The bottom. Why? Gravity. It minimizes its potential energy. Now you have two marbles. They both go to the bottom. They sit next to each other. Happy. Now imagine these marbles are electrons. And imagine the bottom of the box is the lowest energy orbital in an atom. You drop one electron. It goes to the bottom. Spin up. You drop a second electron. It goes to the bottom. Spin down. They coexist. One up, one down. Now drop a third electron. It tries to go to the bottom, but the seats are taken. Up is taken. Down is taken. It hits a wall. It can't overlap. The wave function says no. The probability is 0. So where does it go? It has to go to a higher shelf, a higher energy level. This jump costs energy. Stop. Think about this. The mere act of trying to put a third electron in the same place forces the system to have more total energy. It's like trying to compress a spring. You push, you add energy to the system. The spring pushes back. Why does it push back? Because it wants to release that energy. It wants to go back to its relaxed state. Now apply this to two atoms. When you bring two atoms close together, their electron clouds start to overlap. The electrons in the outer shells start to interact. If the electrons have the same spin, say both UP, they cannot share the same space. They cannot bond. One of them has to be promoted. One of them has to jump to a higher energy state, an anti-bonding orbital. This state has higher energy than when the atoms were apart. So as you bring the atoms closer, the total energy of the system skyrockets. The graph goes up. Nature hates high energy. Nature is lazy. It wants to minimize energy. So what does the system do? It tries to reduce the energy. How? By pushing the atoms apart. This is the trick nature plays on your senses. You feel a force pushing your hand back. You think, magnetic repulsion. But there is no repulsion force. There is only a gradient of energy. The system is simply trying to slide down the hill of energy you created. You pushed it up the hill, it wants to slide back down. The force is just the tendency of the system to avoid the high energy cost of overlapping identical fermions. So, the resistance you feel is actually the universe trying to save energy. But how does this explain why north repels north? Let's look inside a magnet. Most atoms are magnetically neutral. Their electrons are paired up, one down. Their spins cancel out. It's a happy, low-energy marriage. But iron is different. Iron is messy. Iron has lonely electrons, unpaired electrons. In a permanent magnet, these lonely electrons aren't random. They are organized. They are all shouting the same thing. They are all spinning up. Imagine a stadium full of people. Everyone is facing north. Everyone is spinning clockwise. This alignment is what makes a magnet a magnet. Now, bring a second magnet close. If you bring the South Pole to the North Pole, what happens? The electrons see each other. Hey, you're down, I'm up, we can be friends. They can share the same quantum state. They can overlap. The wave functions merge. The energy drops. They bond. Snap. They stick together. But what if you flip the second magnet? Now you have north facing north, spins up facing spins up. The nightmare scenario. The electrons from magnet A try to overlap with the electrons from magnet B. But wait, they are both up. They are identical. The Pauli exclusion principle screams. The wave functions clash. The probability goes to zero in the overlap region. The system panics. We can't be here. We are indistinguishable fermions in the same state. To exist in the same space, one of them would have to flip, but they can't flip. The magnetic domain holds them in place, so they have to go to a higher energy state, the anti-bonding orbital. The energy skyrockets. This is the alignment trap. Because the spins are aligned, they cannot occupy the same space without paying a massive energy tax. The system desperately tries to lower its energy. How? By pushing the magnets apart, by reducing the overlap, by getting the hell away from each other. That invisible force you feel, that springy resistance, it is the direct physical manifestation of the Pauli exclusion principle. It is the universe saying, I will not allow two identical fermions to exist in the same state. And to stop it, it generates a virtual storm. Let's be honest. Everything I just told you is classical quantum mechanics. It's still using balls and waves. But what if I told you that the space between the magnets isn't empty at all? What if I told you it is boiling? Welcome to quantum field theory. In QFT, forces aren't pushed or pulled. They are exchanged. Imagine two hockey players skating on a frictionless lake. One player throws a heavy puck at the other. When player A throws the puck, he recoils backward. Conservation of momentum. When player B catches the puck, he is pushed backward. Conservation of momentum. They move apart. They repel. Did they touch? No. But something was exchanged. Momentum was transferred. Now shrink the players down to electrons. Shrink the puck down to a photon. Electrons don't throw pucks. They throw photons. Wait, light is made of photons. So electrons are throwing light at each other? Yes and no. These aren't real photons. They are virtual photons. A real photon can travel forever. A virtual photon exists for a tiny fraction of a second, borrowed from the energy of the vacuum itself. It pops into existence, travels between the electrons, transfers momentum, and vanishes. It is a ghost particle. The closer the electrons get, the more virtual photons they exchange. The more momentum is transferred, the stronger the force. It's like a blizzard. The closer you get to the other magnet, the harder the wind blows. The more snow hits your face. This exchange of virtual particles is what mediates the electromagnetic force. But remember the spin alignment? When two electrons with the same spin approach, this exchange becomes frantic. The Pauli exclusion principle makes the available states for the electrons disappear. The virtual photon exchange becomes the mechanism by which the universe enforces the no twins rule. The blizzard intensifies. The momentum transfer spikes. The energy barrier becomes insurmountable. So, when you push those magnets together, you are feeling the pressure of a trillion ghost particles slamming into each other, trying to prevent a forbidden overlap. You are feeling the quantum field vibrating with indignation. And this leads to the most disturbing realization of all. If this force is what stops magnets from touching, what stops your hand from going through the table? Look at your fingers. Press them against the desk. You feel the wood. It's hard. It pushes back. You assume you are touching it. Wrong. You have never touched anything in your entire life. Seriously. The atoms in your fingertip and the atoms in the desk are mostly empty space. 99.9999999% empty space. If an atom were the size of a football stadium, the nucleus would be a marble on the 50-yard line. The electrons would be gnats in the upper stands. So if atoms are mostly empty space, why don't you fall through the floor? Why don't you phase through walls like a ghost? Because of the Pauli exclusion principle. When your finger gets close to the table, really close, like angstrom level close, the electron clouds of your finger atoms start to overlap with the electron clouds of the table atoms. What happens? The same thing that happens with the magnets. The electrons in your finger are fermions. The electrons in the table are fermions. They see each other. They panic. We can't be in the same state. To occupy the same space, the electrons would have to be promoted to higher energy levels. This costs energy, a lot of energy. The system fights back. It pushes the atoms apart to lower the energy. That push, that resistance, that is what you call touch. The sensation of touch is just electromagnetic repulsion on a massive scale, fueled by the Pauli exclusion principle. You are hovering, always. You are floating on a cushion of quantum repulsion about 1 angstrom thick above everything you think you are touching. When you hug someone, you aren't really touching them. You are just getting your electron clouds close enough to feel their repulsion. It's tragic, really. We are all islands of fermions, forever separated by the laws of quantum mechanics. So, the force you feel when you push magnets together isn't special. It isn't magic. It is the same force that stops you from falling into the center of the earth. It is the force that gives matter its volume. But it does more than just keep us apart. Let's take a breath. We started with 2 magnets. We pushed them together. We felt a wall. Now look at the universe. Look at a star. A star is massive. Gravity is crushing it. Trillions of tons of hydrogen pressing down. Why doesn't it collapse? Because of the electrons. Because of the Pauli exclusion principle. Gravity tries to squeeze them into the same state. The exclusion principle says no. The electrons fight back. They create degeneracy pressure. This pressure holds up white dwarf stars. It fights gravity itself. And if gravity wins, if the star collapses even further, the electrons get squeezed into protons. They become neutrons. Now you have a neutron star. Neutrons are also fermions. They also obey the Pauli exclusion principle. So now, neutron degeneracy pressure fights back. A city-sized ball of nuclear matter held up solely by the rule that says, I cannot be you. Think about what this means. This repulsion isn't just a quirk of magnets. It isn't just why you can sit on a chair. It is the structural scaffolding of existence. Without it, matter would have no volume. Atoms would collapse instantly. Chemistry would be impossible. Life would be impossible. The universe would be a soup of bosons, all occupying the same state, all clumped together in a single point of infinite density. There would be no structure, no form, no you, no me. So the next time you hold two magnets and feel that invisible springy resistance, don't just think magnetism. Think about the profound truth you are holding in your hands. You are feeling the universe protecting its own complexity. You are feeling the reason why we are here. You are feeling the stubborn refusal of electrons to be anything other than unique. It's not a force, it's a rule, and it is the most beautiful rule in the cosmos.